In this example, we're going to be looking at an example where we're going to be applying both Bernoulli and momentum balance in order to get to our final result. And so this is a good example of how we can use all the different relationships that we've uh, developed in chapter 3 to really pull together a much more complicated problem. So in this case, we're asked first to find a relationship between the nozzle discharge velocity, V2, and the tank free surface height, which is given here as H. And we're told that we can assume steady frictionless flow. And then in part B, we're asked what is the force required to hold the tank stationary? And here, one key is actually going to be remembering that force is a vector. In this case, we only have um, an X and a Y, but there still are two components of that force that we have to solve for in this problem. Okay, so actually I'm going to change that. We're going to say an X and a Z because by convention we tend to label our upwards direction as Z. Okay, so so to get started with here, for part A, the best place to start here is actually going to be mass balance. As I mentioned, mass balance is um, really commonly a good place to get started, especially if you don't know what it is. So we'll say by mass balance, we would have that A1 V1 is equal to A2 V2. Now we're asked to basically solve for V2, and so in this case we end up with V2 is going to be equal to A1 over A2 times V1. But this doesn't incorporate anything having to do with, for example, the height of the tank, right? And that's really what we want to know. We want to know how that velocity V2 relates to the tank free surface height. This is where that steady frictionless flow thing really comes in. Right? That means Bernoulli equation is valid. So to look at that Bernoulli equation, we're going to go from this point 1 to this point 2. And writing this out, we have P1 over rho plus 1 half B1 squared plus GZ1 is equal to P2 over rho plus 1 half V2 squared plus GZ2. Now, at surface 1, we know that the pressure there is atmospheric pressure. Right? This is just the free surface of a liquid in an open container. And now at surface 2, we have an open jet, and we know that for an open jet, as long as it's subsonic, the pressure there is also atmospheric. And so that means that P1 is equal to P2, and therefore these two terms are just going to drop out. V1 is not equal to V2, right, because we have different areas. That's what we learned from the mass balance. So we can't drop out those terms. And of course, Z1 is not equal to Z2. So let's start plugging this in. So what we're going to do is, first of all, start multiplying, or we're going to multiply through by 2 and start gathering some terms together. We're going to end up with 2G times Z1 minus Z2. So we're going to bring that term over. And this is going to be equal to V2 squared minus V1 squared. So 2G Z1 minus Z2 is equal to V2 squared minus V1 squared. But if we, and now we're almost there, right? So we know that Z1 minus Z2 is just equal to H. So this is 2GH is equal to V2 squared minus V1 squared. And now we're going to come back to our mass balance where we had, I'm going to rewrite this actually to solve for V1. So we're going to say V1 is going to be equal to A2 over A1 times V2. Now, we typically assume, in this case, a good assumption, that the area at the surface 2 is much, much smaller than the area at surface 1, right? So we have this really large tank and typically a really small nozzle or hole at the base of the tank. And so if A2 is much greater than A1, then we'll get B1 is approximately 0. And then we end up with V2 is equal to square root 2GH. Of course, if we can't assume that A2 is much greater than A1, or we haven't been given enough information to know that's the case, we can then plug these things back in. And so if A2 is not much greater than A1, then we're going to have 2GH is equal to B2 squared minus, and we're going to take the relationship of mass conservation for V1 and square that, A2 squared over A1 times 1 squared times B2 squared, and that's equal to B2 squared times the quantity 1 minus A2 squared over A1 squared. And then in that case, we end up with the relationship that's V2 squared is equal to 2GH over 1 minus A2 squared over A1 squared. So V2 square root 2GH over 1 minus A2 squared over A1 squared. So either of those suffices for relating V2 back to the properties of this tank, or the geometric properties of this tank, using the Bernoulli equation and mass conservation. But now we're going to go back to the problem statement, and we're asked, what is the force required to hold the tank stationary? Let's start up here. So B, what is the force required? And now here we're going to redraw this, so we can start drawing our control volumes. Our control surfaces. So we have a tank, some hole in it. We know the height here is h, and we're going to draw our control surfaces to be normal to the flow. And now the question is, what is the force that's required to hold the tank stationary? And notice that I'm drawing this force as neither purely horizontal or vertical because it's a vector, and at this point we don't actually know exactly, but we can't say that either of those is 0. So let's start with fx, which, given that we've been looking at momentum balance type problems, might be the place where you would think to start, the one that you would think might be obvious. So we're going to have sum of the forces in x are going to be the sum. So let's see, we'll assume steady state. The sum of the forces in x is going to be sum of m dot v out minus sum m dot v in. And so in this case, we have flow out through our control surface 2, and that's actually the only place that we have x momentum going into or out of the control volume, right? So it's just an outwards flux of momentum through that control surface 2. Remember, through control surface 1, we just have some velocity that's directed downwards in z. So, so some of the forces in x, we have no inlets, right? So no inlets. And the only force that's acting on this control volume in the x direction is the force that we're applying. So we're going to say Fx is equal to m dot times m dot 2 times v2. And I guess by mass conservation with one inlet, one outlet, we know m dot 1 is equal to m dot 2. But we'll put this in terms of what's going on at control surface 2. So we're going to have Fx is going to be equal to um, rho times A2 times V2. That's just our m dot times V2 to account for the momentum flux. And we're going to assume that we have A2 much smaller than A1. I realized down here, I think this was wrong. It's not much smaller than, and here we should be assuming that A2 is much smaller than A1. Anyway, so in this case, we're assuming that A2 is much smaller than A1. So therefore, V2 is square root of 2GH. And so we're going to have that our Fx is equal to rho times A2 times 2GH. Right, so that's the x component of the force required to keep this thing stationary. And now we want to look at the z component. And note that we do, in the z component, for example, we do have some amount of momentum that we're going to have to keep track of, and that's coming into our this control volume. That's actually not going to be the dominant term that we have to keep track of. But let's start out here. So we're going to say sum of the forces in z are equal to the sum of m dot v out minus the sum m dot v in. Again, let's start with our momentum terms there on the right-hand side. In this case, we have no outlets with of the z, right, with the z component of velocity. But we do have an inlet. But we have a single inlet, right? Single inlet. And in terms of the forces acting on this control volume in z, we obviously have the z component of whatever force that we're applying here. But we also have gravitational force, right, which is acting downwards in the z direction because of the weight of the fluid that's inside this control volume. So we're going to assume the tank structure weight is negligible. And that means that the only force of gravity is due to the liquid that's actually inside of the tank. And so if we do that, we're going to end up with F z, right, the z component of the holding force that we're trying to keep track of, minus the weight of the fluid in the tank, right, which is just going to be rho, the density of the fluid, times g, times the volume of the fluid, which in this case is going to be h times A1, right, the area of the tank. And it's negative because this force is acting downwards. And this is going to be equal to minus, right, because we're considering one inlet, m dot times V1. M dot is actually just going to be, you write it out as, for example, rho times A2 V2. M dot 1 is equal to m dot 2. And now this is multiplied by V1. But in this case, so again, if we're going to assume that A2 is much smaller than A1, we're going to see that we're going to simplify that term quite a bit. We know that V1 is equal to, so we know from mass conservation, V1 is equal to A2 over A1 times V2. So So, but um, therefore, we're going to end up with fz minus rho g h a1 is equal to minus um, rho a2 times b2 squared times a2 over a1. But if um, a2 is much less than a1, then this term is going to drop out. This whole thing is going to drop out. It's going to be approximately 0 if a2 is much less than a1. And so what we're actually left with is that fz is equal to rho g h times a1. So the force required to hold this container stationary in the z direction is basically just due to the weight of the fluid that is inside of the container. So that's a result that should make sense. So there we go. So this was an example of how we can use mass balance, Bernoulli equation, and momentum balance to solve a problem that is a little bit more complicated than some of the very simple examples that we've looked at in class and in some of these other videos.